but I think it's very nice. And I've known Fabio. Sorry, I've been knowing. I think I met the first time Daniel maybe 2015, so it's almost 10 years. And he is one of the greatest presences we have in our field, and I consider him a great friend. We haven't worked together yet, but it's very nice to be here and honor his company. So now back to business. As Fabio was commented, I will talk about lattices from Fermat function fields. This is a joint work with Rafael. So Rafael is my master's student. Actually, now he's my PhD student. So most of the things we are saying here are contained in his master's thesis. And it's kind of a new area for me. I will comment how we got there. And well, without further ado, I hope you enjoy. Let's go there. So what we're talking about, f of x and y will be an algebraic function field. And most of the times I don't need it, but defined over a finite field. Right, give it some kind of power. We will denote by G the genus of F, and we will be dealing with the places. And specifically what we are interested in, so as the title says, we will be dealing with lattices. So as you can imagine, we are going to give kind of explicit construction of some lattices arising from function fields. So for the people who are usually work with curves over finite fields, the first things you think of are, well, codes, of course. And those are usually valuation codes done via, or geometric Gopa codes done via remote. But in this case, we'll be dealing with something slightly different. So Riemann rock space will play a little role in the end, but it's not really the kind of object we're interested in. So say that we have P, P1, Pn, a set of places. Of that, and we are interested in this kind first in this set. So the set is the function in F such that the valuation of P of F is 0 for each place is P, which is in a set of places, let's call it capital P. Minus small p. This should be this divided. So this sounds kind of artificial. So let's give, for instance, an example. Let's start with the Fermat with the Hermitian function field y to the q plus y equal x to the q plus 1, and I will choose as p the set of fq square rational places. Of each. So it's known that you have qq plus 1 places. Of course, this is maximal in the most symmetric maximum function field at the highest genes among the possible maximum function fields and so on. So then, for instance, what is the relationship we may inquire between places and functions? So which function f here I associate a divisor, which is a formal sum of places where ni is 0 for all but finitely many. Places, and I say that P is a 0 of f if, and this ni is the discrete valuation associated to Pi. P is a 0 of f if the valuation of P of f is bigger than 0, otherwise is a pole of f if this valuation is smaller than 0. So valuation behave nice with respect to multiplication. What do I mean by that? That I have f and g functions, and I want to know the valuation of P of f times g. This is actually the valuation in P of f times, plus the valuation of P of g. So for instance, if we take here the Hermitian function field, what is the divisor of x? Well, the divisor of x is 0 plus EQ minus q times infinity. What do I mean by that? Is you may think of this as the Hermitian curve, actually. So in the affine plane, you have q points, and you have just one point at infinity. So infinity is the unique place at infinity. Or so you have the divisor of y. Well, this is nicer. Q plus 1 is 0 minus q plus 1 infinity. As you can see, this is not actually a coincidence, because if I say that the degree of a divisor is simply the sum of its entire. So if I have the divisor of a function and I inquire about its degree, it's 0. The sum of the poles equals the sum of the sum of the multiplicity of the poles equals the sum of the multiplicity of the 0. So for instance, here I may inquire about the divisor of x and y, and so I have just the sum of the divisor of x plus the divisor of y. This suggests a nice trick that I may want to do. So consider, for instance, here now this homomorphism. So it's easy also to see that if I take fg in this OP star, then f times g is in OP star. And also the inverse is well behaved. So in particular, if I consider this guy, this phi from OP star to say z to the n, which to its function f invariant sense, where this n is to be determined by this n is this n here where it is. Just pp1 of f, pp1 of f, well, with ppn of f. This is a group of them. So I start with a set of functions, and I end up with vector into some Rn to the n, say, with integer coordinates. Well, so this is a natural way. So the image of it is actually the lattice associated with the function f. So for reference, like just to be more clear, what is a lattice is a discrete additive subgroup. Of R to the n, or if you think, you take say B1, Bn linear independent vectors, and then you consider, say, the lattice lambda is the set of combination A1, B1, plus Am, Bn, where these G for I are just set. So when you see, if you come from the area of studying codes from curves or from function fields, you know that one of the reasons these codes are well studied is that you have a nice intuition via Riemann theorem of the minimum distance of these codes. So in this case, of course, you have to consider for a vector being lambda, you consider the norm of it, which is actually the Euclidean norm, and the minimum distance of the code, say t of lambda is just the minimum of the norm of V such that V is lambda. So do I have something similar here? Well, here is actually easier if you think about that, because what is the lowest case I can have? So you think I have this bunch of places, and I just take a function. I just have to see. So say that it has neither 0 here, so it has 0, and then I get to the first 0. Well, to minimize the Euclidean norm, well, I just have simple zeros and simple codes. So this leads us to introduce the sort of this symbol, gamma of f, which is called the gonality of f, which is the minimum of the degree of a function f for f in all p star. So you may ask, what is the degree of a function? The degree of f is just the sum of the, or say, API of f bigger than 0 of the API of f. So for instance, if a function has, like, say here, what is the degree of x? Well, this simply is the same as the whole. So x has degree q, y has degree q plus 1, right? If you come from algebraic geometry, you might think that this gonality is not the gonality of the curve, because this depends on the set of points you are taking, right? But in most of the cases, you have this is actually the gonality. So when we first started studying this, we were to see in the literature. So this is pretty simple, right? And actually, this definition has been around since the early 90s, which has been introduced independently by Vlad, Rosenblum, and then it stayed silent for a while. Then people started to be interested in this kind of construction, and they started to use elliptic function fields and Hermitian function fields. In these two cases have a very interesting feature, which is that the lattice is coming from Hermitian function fields are, well, what does it mean? Well, actually, there are a few definitions in the literature, but here you see, so this is the z-span of m vector, and so this m like that is the rank. And a lattice is well rounded if contains m linearly independent lattices. Sometimes it is if it's spanned by m linear independent vector over C, so it's kind of more complicated. So for a while you say, wow, maximal curves, elliptic curves give me where around the lattices are interesting for applications with cryptography, etc. So you say, oh, maybe I have found the maximum to wear around in this. Actually, no. Because later came Fishnot and lattice, which gave which studied a little bit further what does it mean to have this kind of construction. And they saw that in general, you have no hope for world randomness. And for a while, that was the end of the story for this kind of construction. Also because if you have seen something about the median varieties of Jacobian occurs in your life, you have seen something which is called the subgroup generated in the Jacobian by a bunch of points. And this bad boy here, this OP star, is a huge protagonist in this. So actually, these are just words. These kind of lattices we're doing are actually sub-lattices of the lattice on the Jacobian variety of this curve. Those have a bad advantage, are always corrupted. But the minimum distance shrinks. So when we started studying, we focused on the fact, so I have, here I didn't say here, but what is an obvious lower bound here for the minimum distance? 2 square root of n. And all the examples in the literature attain this lower minimum distance. So we started to think, well, can we do better? Can we find lattices that beat this lower bound? And this is maybe the punchline of what we did. So start with the Fermat function field. Say Fn. So now, as you have seen, I didn't enter into details, but for what I talked here, so when I talk here about the lattice associated with the Hermitian function field, well, I'm talking about when the set of places is all the F2 square rational places. So here we did something different, and we chose as P Fn intersected x, y, z equals 0. So basically, this is a triangle. Just taking so here we have 3 points. And the interesting thing here is the following. We had some previous knowledge on OP star due to Roglic, which in the early 90s studied this set of functions in characteristic 0. Because it wanted to compute the subgroup generated by these 3 endpoints in the Jacobian. And the punchline here is that the minimum distance of this lambda associated with Fn is bigger than the desired minimum distance. And the reason behind this is also the fact that maybe it's given to the fact that we have too few points. Just a little thing here. What is the gonality of Fn? It's actually a -1. So because the point is here, these points are what's it called? Total inflection points. So the intersection multiplicity with the tangent is actually the degree. Then you cut by another curve which is on tangent, and you have a function of degree -1. Well, actually, the minimum distance of the lattice is, well, not really exciting, still n instead of 12 plus or -1, but still. Also, you may be interested, for density reasons, you want to count the number of minimum norm vectors. And this is called the Kissing number of lambda. And what we proved is that independent of the usually when you have this kind of construction, the Kissing number sort of depends on the rank. But here, no, we prove that K of lambda of Fn is actually 6 for n at least 4. So you don't have a good density actually. You have few minimum lengths. And one thing that might be interesting here to see is that, so you may say, what's next? I'm not giving the details, but like the techniques are pretty standard actually. Because when you think about that, so here I say, well, if I have, because the first thing to prove is that you don't have any minimum norm function. But the minimum norm function must have the whole divisor, like a sum of simple points. In particular, this function must belong to a Riemann rock space, because you have a total control of points. And so basically we have to prove that a certain Riemann rock space has dimension. So what can be next in this kind of study? Of course, we would like to say more on these ones, because for instance, for application to cryptography, you want to know the second way. So you have the minimum distance, second minimum distance, and distribution of words of vectors of minimum distance. You may want to know the density, the determinant of the lattice, and the determinant of the lattice actually is the reason why, because I already expected the question, where do finite fields come in hand? Because nothing seems to have to actually do with finite fields. I can do it in characteristic field or over algebraic field. The reason is that for the determinant, you need to go to the class group. And so you have to be sure that this is a finite group. And that's all you have to use that you only have in characteristic when you have a finite field. Of course, if you happen to work in characteristic 0 and the group you're constructing is a finite group, as it's the case here, it actually doesn't matter. How much time do I have?
2 minutes.
2 minutes. So another thing which is interesting, so more things can be done, of course. This will be part of Rafael's PhD project, so I'm not going to give much more spoiler. But one thing that I want to really understand, which has been really sub-explored, is the relation of lattices with what happens in the Jacobian, which still is kind of mysterious to me. Because it's not so immediate for me. Because here, for instance, you have that in the Hermitian, you have the gonality of the Hermitian is Q, but then the points, which are you consider generate Q plus 1 portion in the Jacobian. So apparently you don't have. I don't really see what's happening there. So that's one thing that I would like to understand better. And of course, and this also same. It's not exactly a new application of functional physical curves over finite field, but it seems a sub-explored application. So I think it's nice to play around with. So I think I will stop here. Thank you very much for your attention.
Any question?
Thank you. Very nice talk. Okay, if I'm not mistaken, you took the Fermat curve and you showed that with these points, these photon inflection points, you construct the lattice and it has nice properties. Okay, and okay, but I don't know. The rank of the lattice, I didn't get. I mean, of course, you can take the Hermitian curve. You can choose a different kind of subset of the rational points and obtain different parameters. I mean, can you say the role that the rank plays on that? I mean, you desire nice properties with the big rank or small rank, it doesn't matter.
So,
You get my question?
no, yeah, this is actually a very good question, and I think it's the core question. The point is, I hid some things here. And the point is, because for instance, what the Akin association proves is that actually most of the things that you can prove are actually related on the number of subfields of degree diagonality. So one of the reasons why Hermitian works so well, so the gonality is Q, and of course you have a lot of subfields of degree Q here. So that's why this Q plus 1 points work very well. But at the same time, it depends a lot on what you want. For instance, why elliptic curves work well? Why? Because they have a lot of subfields of degree 2, which is the gonality. But if you go to a hyperelliptic curve, in the degree of at least 5, then you have only one subgroup, only one subfield of degree 2. So that's why they say here you don't have no homover roundedness. You have, but you have just one subfield, so you lose a lot of progress. But what you can do is, okay, take away the ramification points, take away the points with matter for the subfield, and then you have another gonality. And then you may play around a little bit. So one of the key points here is also this. In general, this subgroup of functions that meeting we control poles and zeros is kind of mysterious, because you don't have it completely explicit for a lot of curves. So for instance, when you start with elliptic curves is sort of easy, because basically what you're doing, you're working on the group structure of the points. So you have extra information. For the Hermitian curve, one thing that they use is that every function in OP star, which P is the collection of all the square rational points, can be expressed as a product of lines and inverse of lines. So there's all the information here. Here, of course, the set of, so in general, I would say you need a big set of points, but not too big. And here, when you say generic Fermat function field, of course, we started here because, well, part of the work has been done already. But here, what's important is you have few points. So any function of minimal degree doesn't have space to have all of these nice zeros of degree 1. Of course, it may also inquire here, for instance, you have the Leopold points, which are the points fixed by evolution, which are always large first points. They may ask the same question for these points and see what happens. In general, I would say that if you take point, if your P is a subset of Weisser points, you have already something. But that's just an indicator.
I would say, in general, the set of Weisser points is small compared to. Well, no, more than. And
it's bigger. 3. Yeah. Yeah, in this case, for matters.
Okay. But
so,
and it has been for a while. People did lattices, you said, and so people didn't. I mean, another like comparables, like because they had other furniture, some people didn't try anything.
So my conspirational theory, la mia teoria della cospirazione, is that the two things that made people stop considering this, actually 3 things. First, the fact that they are realizing there were sub-lattices of some other lattices on abelian groups, and so they moved to this one because those are always well-rounded. Also, because Stishno proved that it's hard to have well-rounded here. And also because in general, I mean, you don't have that much information about this OP star, so you basically have to do the work before to understand this function, and then you construct the lattice. Actually, you may have twin works. You see the second function, then you construct the lattice and the group generated by those points in the group and see what happens. But in general, it's difficult.
Yeah, maybe it gets nothing there.
Might be. But we are going to dig deeper into this. So hopefully we'll have further interesting things to say in there.
So, so lattice, there is a whole area of lattice codes. So this exists for a long time, and you do selections of the lattices through basically construction, an A, B prime, everything is explained in the book of Sloan, packings and lattices and so on. And so it exists the whole area of lattices, and in particular these known techniques and algorithms for doing the coding of those lattices. Basically, a code word is a lattice point, an error is an array that is not, and then you need to find, you suppose, a small number of errors, so you go to the closest lattice point. And how do you do that? Well, those are the algorithms and so on. And my question here is that it has been shown, someone studied how this construction of these lattices compare to those. Like, for example, in the case of those lattices, there are many results on the codes that can tell you things of the parameters of the codes. So I really wonder myself, and maybe some of you know, I don't know, for your student, right? To maybe understand how this compares to this other area, right? There may be something here to show that maybe, yeah, sure, you have this issue that you were saying, but maybe there are other issues. Forgetting a little bit about crypto application, this is purely cognitive. You don't care at all about shortest vector, largest vector, the thing that you care, in crypto, right? Yeah. This is coding theory purely. So then you say, well, how good is this lattice? And good for coding theory means if you fix some parameters and you vary one, how optimal you are on that. Normally, distance or even length. So I wonder what will happen if you grab one of these and then really do a comparison for the same type of dimension, same type of parameters, and see maybe there is something that is that could be good, that could be comparable, or not. Maybe say no, really this lattice is loose.
Yeah, I mean, I don't know. We didn't look into that, but it's something we're really interested. Actually, I wanted to mention before, but these were originated by a series of seminars that we had with Sueli Rodriguez Costa's group at Unicamp, where we presented something we know and then the same. So I would like to explore this further. So that's really interesting. I hope to have an answer in the future. But as far as I know, it has not been done.
Yeah. No, my other point was in Campinas, you don't need to work very far. So,
just the office next to mine.
Any other question? Comment? Something like that?